Hi, welcome to your lesson on quadratic sequences when the leading coefficient is not 1. Okay, take a look at this sequence. What kind of sequence is this? I hope you noted that that is a linear sequence. The reason for that is when we write up the sequence and look for the common difference here, we see that there's a first difference that is constant. That always tells us it's a linear sequence. In other words, when we go from one term to the next, we are always adding or subtracting the same number. In this case, negative 7.5. Therefore, our rule is this. This is called our common difference, or if we're graphing it, this would be a slope. And over here, we have our y-intercept, or our starting value if we were at term 0. Here's term 1. If we're going down 7.5 here, we would go up 7.5 to get to the previous term, which would be term 0. And that is always the value that appears here. That's a recap of what we've seen. Let's keep going. We learned an important rule about quadratic sequences. That linear sequence was just to recap what those were, but now we're talking about quadratic sequences. And we learned an important rule, and it is this. In a quadratic sequence of this form, okay, quadratics always have a variable squared, in our case, n squared. If a quadratic takes on this form, the coefficient of n squared, that means the number in front of n squared, in this case the c value, is always half the value of the second difference. What does that mean? Well, let's say we had this quadratic sequence. We can see in this quadratic sequence we do not have a constant first difference, but we do have a constant second difference. Again, that tells us this is quadratic, but now the more important part in this rule is that since we know the common second difference here is 6, that means the rule will have a coefficient here in front of n squared that is half what we see here. We see 6 here, therefore 3 in our quadratic rule. Let's look at another one. Here we have another quadratic sequence. Here's our first difference, it is not constant. Here's our second difference, which is constant. In this case, we see a negative 8 as our constant second difference. Therefore, when we write the rule, we have a half that value, negative 4, as our leading coefficient right here. That's a key rule, so make sure you pause and absorb that rule some more. Now let's move on and apply it. So again, those constant 6's tell us there will be a 3, and these constant 8's here tell us this will be a negative 4. All right, take a look at this sequence. What kind of sequence is this? Okay, I hope you noted it's quadratic. If we write it out and look for the first difference, we get these values. And then a second difference is 2 here. So since we have a constant second difference of 2, what does that tell us? Well, first there's a sequence. What does that tell us we will write right here? What will we write here? Well, I hope you came up with 1n squared, because when we're finding a quadratic sequence, it helps to have our table of values. And we know, since we see a 2 here, that our leading coefficient will be half of that, which is 1. So we'll have 1n squared here. And of course, we can just write n squared. Now, what does n squared produce? Produces these values. Then you follow the process we've been studying, which is to find the difference between that. N squared produces 1, but we need negative 15, therefore minus 16, and so on. Now look at these, and these should make a linear rule. So now, what is the linear rule for this? Combine it with n squared and tell me what the final quadratic rule should be here. Well, in the linear portion, we see a constant first difference of negative 7, so that means a slope value of negative 7. Therefore, our rule is n squared, or 1n squared, and then our linear rule is negative 7n with the slope there of negative 7, and then a y-intercept here of negative 9. Because if you jumped back to term 0 of this sequence, jump back one term, you would be at negative 9. Okay, let's try another one. So here's the image you saw in the opening slide of this video lesson. You can see a sequence written here. It is quadratic. So go ahead, go through the process, and come up with the rule to model this quadratic sequence. Let's check. So here's our sequence. We have a first difference of 3, 5, 7. That means we have a constant second difference of 2. That 2 tells us that the leading coefficient in front of n squared will be half of 2, which is again 1 right here. Fill in the table. And again, this is one of the simpler ones. When we see a 2's here, we know it's simple because we have a value of 1 in front here. So now we look for the linear pattern here. In this case, we needed to add 3 every time to turn our simple quadratic into our actual sequence. So if we're adding 3 every time, our rule should be this, because n squared plus 3 gives us what we need every time. N squared plus 3 gives us what we need here. N squared plus 3 gives us what we need. Okay, there's a basic rule. We have no slope. If you were to graph this linear thing here, 3, 3, 3, it means the y value is always 3. So imagine a horizontal line which has an equation of y equals 3. And that's why we have just 3 here and no n. Okay, let's keep going. There is a practice assignment that follows this video. It looks like this. You might want to take a screenshot or photo. Those are the problems you have to complete. I gave you key problems to focus on. If you want to learn more, you can try all of them. In this video, however, we're going to look at K, E, and L together now. So let's see if we can create rules for K, E, and L. Here's K. Give it a try. What would be the rule for this one? Let's take a look. Here's our sequence. We have a first difference like this. Therefore, our second difference is a constant value of 4. That constant value at our second difference tells us it's quadratic. And since we have a 4 here, we know the leading coefficient, the coefficient in front of n squared is going to be 2, right? Because it's always half of what we see here. So 2n squared. So now we fill in our table here. Here's the sequence we want. Here's what 2n squared creates. So we put 1 in here. 1 squared is 1 times 2 is 2. Then we put a 2 in for n. 2 squared is 4 times 2 is 8. And then next one, put a 3 in there. 3 squared, 9 times 2, 18, and so on. Now what's the difference here? Let's make our linear sequence. There's our linear sequence. We need to subtract 3 to get what we want here. Subtract 7 to get what we want. Subtract 11 and onwards. What's the rule for the linear sequence? Well, I can see that linear sequence. Well, first of all, 2n squared is our quadratic part, and then we're going to add the linear part. So what's the linear part? Okay, I hope you came up with negative 4n plus 1, because this linear portion in green is going down 4, down 4, down 4, a slope of negative 4. So there's a slope, negative 4. And then if you went back to term number 0, you would be adding 4, and that would get you to 1 as your y-intercept here. Okay, try this one. In this one, I put the sequence in. Here's our our first difference, which is not constant, and then our second difference, which is constant, 6's. So again, I'm going to put the sequence in here, and then I'm going to write what here. Well, that should be 3n squared, because we always take, again, the rule is half of our constant second difference gives us our coefficient. There's our 3, and now we can fill this in. So 1 squared is 1 times 3 is 3. 2 squared is 4 times 3, 12. Filling in the table by putting n values into here. There's that. Now find the difference. Oh, look at that. Constant difference. All right, we always have to subtract 4 to get the sequence we need. So what's our rule this time? Well, we know it's 3n squared plus something. What's our linear rule? Well, it is just negative 4. Just like the one we saw recently, this is always negative 4. So it is just a horizontal line at negative 4, and it's just negative 4, because 3n squared minus 4 will give us what we need every time. 3n squared minus 4, 3n squared minus 4, and so on. 3n squared minus 4. All right, try L, the last one of the ones from the practice assignment we're going to look at together. This one has decimals. It might be slightly more difficult. Let's see if you can do it. Okay, here we go. There's a sequence. There's our first difference. Now I'm looking for a second difference. In this case, constant second difference of 2.5. Okay, so fill in the sequence, and now what goes here? That should be 1.25 n squared, because we take half of that to get the coefficient. Half of 2.5 is 1.25. Okay, now you're putting 1 in here. 1 squared times 1.25 is 1.25. 2 squared is 4. 4 times 1.25 is 5, and on and on. All right, now look for the difference. Here's what our 1.25 n squared produces. Here's what we need. How much more do we need? 1.75. How much more do we need here? 3. How much more do we need here? 4.25. This is a linear sequence. What will the rule be? So our whole rule is going to be 1.25 n squared plus the rule for the linear portion. What is it? Okay, I hope you came up with this, because we have a slope of 1.25. It's going up by that constant amount every time. And if you back to term 0, if you went back, you would get this. Great job if you got that one. It's always a little tougher with decimals. Now let's jump to the challenge problems that we began during our lesson. So they are in your packet of problems, and we're going to try those now together. Problem 1 was this one. We have a quadratic sequence which has a first term 4 and second term 10. The coefficient of n squared is 2. That's a big hint here. Okay, what are the next 3 terms? What did you come up with? Great. Maybe you got it already, maybe not. Here's a hint to start. We know 4 is the first term, 10 is the second term. What are the next ones going to be? That's our goal. We are given that 2n squared is the beginning of our rule because it says the coefficient is 2 for n squared. When we're given that, we know the second difference must be 4. Right, because it's always double that. So if you begin with your sequence 4 and 10 here, okay, let's see, the difference between those is 6. And then we don't know the next numbers, but we can go down further. We know the common difference is 4 for your second difference, because that's what we're given through this statement. So I put a 4 here. So now 6 plus 4 will give us this next value here. What's it going to be? 10. And now to get this one here, we're going to do 10 plus 10 to get this value, 20. Great. What's the next one going to be that we can get? Well, we can put 4 here again. 10 plus 4, 14. Then 20 plus 14 must be 34 here. Let's put another 4 down here. 4. 14 plus 4, 18 here. 34 plus 18, 52 there. Great. So we have found the next 3 terms. They are 20, 34, 52. Okay, let's try the next one here. You are given a visual sequence. It's called a triangular sequence. We have 1 dot there, 2, 3, 4 dots. Okay, we need a rule for Tn, T sub n, which represents the number of dots. Okay, so when n is 1, we have 1 dot. When n is 2, we have how many dots? And then how many for n is 3 and 4 as well. Okay, so hopefully you filled this in as your sequence. When n is 1, 1 dot. When n is 2, 3 dots. When n is 3, 6 dots, right? And when n is 4, 10 dots. There's our sequence, the one you're trying to find a rule for. Try it now. Okay, so I found the first difference, which is not constant. And then I went down another level. Second difference, 1. Constant, second difference of 1. So what is the coefficient in front of n squared going to be? Okay, the coefficient then is half, because it's half of that. So half n squared is what we're doing. Here's our table of values with the half n squared. And in the end, I have a linear rule that also has halves there. Okay, so this one's a little more complex, but there's our rule on the bottom. Half n squared plus half n. A little bit tougher. Maybe you found it a little more challenging. But basically, yeah, here's our quadratic. Here's what needs to be added. That's a linear rule with a slope of half. And if you go back to term 0, it has a value of 0, so we have nothing here. Think about that one if you struggle with it. Look at the numbers closely and figure it out. Let's go to the next one. This is problem 3. You are to create a rule for A, B, C, D. First one is the perimeter of these ones. And then, oh, wait, sorry, this is all one sequence. Make a sequence for perimeters, and the value is actually given to you. 12, 12, 20, 28, and so on. And then another rule for the number of shaded squares, and that's given to you as well, 4, 8, and so on. And the third pattern, number of unshaded squares, is given here also. And then the total number of squares. So 4 different sequences. Okay, check your work here. First 2 were linear. You should have noticed they're going up by the same number. For example, 12 to 20 is 8. 20 to 28 goes up by 8 again. Constant first difference. Second one, 4 turns into 8. 8 into 12, it's going up by 4 every time. We can see that here. But the last 2, the unshaded and total squares, follow quadratic sequences, and these are the rules you should have come up with. Great job if you got that. Next one. I love this problem. I always love applied problems. This is a very real kind of situation, and when we solve it out, we will notice it is a quadratic sequence, and therefore we can make a rule to predict the future. So take a moment to read that. Great problem. Okay, let's introduce this great problem here. We have a group stage of a volleyball competition. All the teams in the group have to play each other. So if you've been part of team sports, you know how this kind of thing works. You have a bunch of teams, and you have this thing called, sometimes called a group stage or a round robin, where every team must play every other team. So when there are 4 teams in a group, 6 games are needed for each team to play each other team exactly once. How does that work? Okay, well, let's begin with, okay, so here's the number of teams we can say we had in the tournament. So if we had just 1 team in the tournament, well, how many games would they play? The answer is 0, so we could put a 0 here, because 1 team can't play itself, so there's no games. If we had 2 teams in the tournament, how many games would they have to play in order to play every other team? Well, there's only if there's only two teams, then there's only one game that takes place, so that'll be a 1 here between those two teams. Okay, now what if there's 3 teams? How many games would they have to play so every team plays each other? And you might want to write it out, like call them team A, B, C, and say like, okay, team A plays B, team A plays C. Okay, what are all the possibilities? So how many games will take place here? And then 4, it told us if there's 4 games, there'll be 6 games needed. How about 5? How many games would be needed if there's 5 teams in the tournament? Okay, so here are the numbers you should have. I hope through that quick discussion of those columns there, you're able to understand what that represents. That is the sequence that we are now trying to find a rule for. So when it says find the number of games needed for each team to play, when there are n teams, right? Whenever we say n teams, we're saying some unknown number of teams. So we want to create a general rule that we can then use to find out the number of games for any number of teams. So find a general rule. Okay, so I went to the first difference, I got this. I went down 1 more to second difference, I got that. Okay, when the second difference is constant, it's quadratic. And we know the leading coefficient, because we see a 1 here, must be a half. So half n squared is how our quadratic rule begins. Go ahead and fill a table, make it work. Let's see what rule you come up with. Okay, here's what I did. Here's the sequence. Here's half n squared and what it produces. And then I did the little difference between what I get from half n squared and what I need. That is a linear sequence with this slope. And therefore our rule is this, half n squared minus half n. Is that identical to that last couple problems ago? Maybe, close to. Anyway, great problem, great way to take some words, change it into a pattern, which we can then express mathematically. Now you can use this rule to find out the number of games for any number of teams. Okay, next one. This is also another great problem. If you're here listening, I'm glad you've arrived at this moment. Let's try. We say we have a quadratic sequence that begins like this. We are looking for the value of x. Okay, so there's some unknown value there. Of course, you can guess and check a bunch of values and see if it works, but let's use some algebra to approach this. Let me remind you of how we deal with these, right? If we had a sequence and we're trying to find this common difference, or this difference here, first difference, we see 3 to 5, 8, right? We can do 8 minus 3 to get this number. So we always do this term minus the preceding term. So if you were to find the one right here, you would do this term minus this one. So what would go here if we're doing one of these little tables here? Well, that would be x minus 3. So is that one minus that one. Great. Do the same thing here. I hope you got 29 minus x. How about over here? That's 22, which was 51 minus 29. Great. That's the first difference. Since this is quadratic, we're going to go all the way down to the second difference. Okay, so to find the second difference, same thing, right? How do you find this value here? Well, you find it by doing this term minus this one, right? So what is this minus this? Well, I wrote it out here in full, right? 29 minus x minus, and parentheses here are important, because if we're subtracting all of this, that negative has to apply to the x and also to the negative 3. So you need the parentheses to do the proper algebra after. Okay, so what goes here? Okay, 22 minus this one. Now, this is a big step with this one. We have no numbers, but we need x. We just have these things with x in them. Okay, but what do we know for quadratics? The second difference must be constant. That means if this was a number and this was a number, those numbers would be the same. So if this is the same as this, we can do what with these? Well, we can equate them. We can say that thing equals this thing, because those numbers must be the same. So this equals that. That's what I wrote. Now use some algebra and solve that. You can get rid of the parentheses by multiplying by negative here, also here. So let's see if the algebra takes you to the right answer. You should get 13. Check your work. The mistake students commonly make is here, right? The negative applies to the x, so see here, negative x, and the negative applies to negative 3, it makes positive 3. The same over here, that negative makes the 29 negative, but it also applies to this negative, which makes it positive x. And then it's a matter of combining some things, moving down, you got the answer. Take a look if you need to. Next one, and the last one. Another very good problem, and it's going to lead us into a little proof in just a moment. Here we have, it says there's a second difference rule. We've learned this way of dealing with quadratics, right? We look for a second difference and move on from there. But there's another kind of shortcut. There's a shortcut that looks like this, that if we have this quadratic statement here with c being the first coefficient, b the second coefficient, and a the last one, we can have this rule, which is always true, that 2c will equal this one, the second difference number. 3c plus b will always equal this first number here, and a plus b plus c will always equal that number here. This rule always works. So if you have any quadratic sequence, you can write these letters like that here. And that helps us actually solve what c, b, and a are. So we can begin in the bottom. If 2c equals 4, then what is c? Well, if 2c equals 4, then c must be 2. That means this number will be 2. And that makes sense. We know that. When we have a common second difference, or a constant second difference, the value in front of the n squared will always be half of that. So c, you can see here is 2. That means the 2 will go there. That makes sense. We knew that already. Now let's jump up a level. 3c plus b equals this first number. Okay, let's start with that equation. 3c plus b equals 13. Well, we can't solve that because we have c and b, but we just found c. So why don't you take the c thing we just found, put it in there, and solve for b. Okay, so 3 times 2, because c went in there. Solve that. B is 7. Okay, so we just found out this number is 7. Okay, let's jump up to the upper level here. A plus b plus c equals 5. It always equals that first number in the sequence. Great, now we know what b and c are from before, right? C and b, we got them, so plug in your b and c and solve for a. Okay, b went in there, c went in there, solving for a is -4. It's as easy as that. We just found out the rule must be 2n squared plus 7n minus 4, because we have our c, b, and a values here, and we just put them in here. Seems pretty simple, but we in math, sometimes there's shortcuts like this. That's so much quicker than what we did with the table and all the rules we did, or the approach we took. Our approach, though, is very sound. This one is just a matter of memorizing these. Or is it? We shouldn't memorize in math. We should always look for why. Why do these 3 rules work here? So the next slide is going to be a little bit of a challenge, but I know you guys are up for a challenge. We're going to show where this idea came from. Okay, so here's the idea I was just showing you, this shortcut. Let's say we begin with a general quadratic that looks like that, right? That's what we've been talking about. Now, if you found u1, that means 1 goes in here, 1 goes here, 1 goes here. The first term, we're looking for the first term. So I put 1 in here, I put 1 in here. This simplifies to c plus b plus a, because that's 1, so just that. Okay, so the first term has to be c plus b plus a. Okay, u2. Now we put 2 in here, 2 in here. See, 2 goes in here for n squared, 2 goes here. Simplify that. 2 squared is 4. So that becomes 4c plus 2b plus a. Okay, and now I'm going to do u3. u3 means that third term, we're going to put 3 in here, 3 in here, 3 in here. 3 squared, 3 here. That simplifies to, oh, do I have it? Let's see. Yeah, there it is, 9c plus 3b plus a. So now we have our first, second, third term. I'm going to put them in here. First, second, and third term. Exactly as we had here. There's our first 3 terms in any general sequence like this. Okay, there's no numbers. It's just these letters that represent numbers. But there's our first 3 terms. They'll always look like that. Now, go down to the second difference. The first difference right here. And remember, again, when we find the first difference, to find this number down here, we always do this second term minus the first. So find this one right here. What would this minus this come out to be? I hope you got 3c plus b. Why? Because when we do this minus this, we're doing 4c minus c, which is 3c. We're doing 2b minus b, which is b. And we're doing a minus a, which cancels. So we're left with this. How about this one? What's this going to be? Hope you came up with that, 5c plus b. Now let's go down to the second difference. What's going to be down here? 2c. When you do that minus that, you get 2c. And now look at what we have. First term is a plus b plus c, and that's exactly what we saw here. The first term always equals that. Second term, the next one down here, right, when we make the little table, that 13, is equal to 3c plus b. That's what we see here. And then the second difference, the common second difference, 2c. That's what we have here. So there's a derivation of this shortcut, and now you know. Great job. We'll see you soon. And of course, don't forget, there's more to practice. If you got some energy left and you want to become a master, go back to our problem set. We already did E, K, and L. See how many more you can do. Great job. See you soon.